Last time we started a little bit discussing Bochner spaces, that is function spaces which live on a time interval but have their values in other Banach spaces, which is supposed to mimic then the spatial dependence of time and space-dependent functions. And we have introduced the LP spaces, and in a second step the W1P spaces. These are the correspondence of the, so to speak, classical Sobolev spaces, seen various relationships. And now what we still need is a relationship to the space of continuous functions, because we need continuity in time to express in a strong sense what does it mean that such a solution obeys an initial data. We can introduce and have introduced already a notion of a trace in time, which goes just by partial integration. So we integrate, we need corresponding test functions which allow this point in time where we want to have the trace to be in the support and not the final time, such that only one boundary part, which is just an evaluation here in for the time interval, appears. So this we can also do, but if we want to have a strong notion of an initial data, we need continuous functions. So we need something like, so the general situation is X is a Banach space. If there are any doubts, it is also reflexible. For some results we need reflexible. For some results we need this, as we have discussed. So not for everything. So we have our time interval, let's say 0t. Of course it need not to be this initial point is the time interval. So this is the general setting. And now we look at the space C0 on I with values in X, which just means as we are used to have it. And so there's no new consideration concerning measurability or things like that necessary, because continuity is a notion which we can write down in general, having Banach spaces, having, so to speak, 2 bars instead of 1 bar for defining the distance. So we have here all those functions which are continuous. Oh good. Okay. So the norm correspondingly is what we would also in the scalar case define as a norm. And in this norm we then also here get a Banach space, as in general all those spaces which we have introduced turned out to be Banach spaces. So the norm is just take the supremum as usual, but now it's not the modulus or a vector norm, it's just the Banach space norm of the images, and we go over the full, here we have then the X norm, and here we go over the full interval. And we have discussed already the fundamental calculus of differentiation and integration, if you want. And in the general case, if a W, what turns out here is, in general, we have this situation. So if we integrate, if we have the time derivative in some weak sense, and let me remind you the way we had it. Or didn't we have it already? So maybe we have not yet touched upon this. So what we now here can put down, so as we have here in a general case, we only have this fundamental theorem for almost all instances in time t1 and t2, and here, because of the continuity, we have it in general. And that means, in particular, an embedding theorem. Maybe I write it down. It's the following, so the general assumptions. So what do we need? We need a u from L1, 0t, x. We need its derivative. If I write down the derivative, I always mean the distributional derivative, which can be represented by a function, and the function is supposed to be, again, an L1 function, 0tx. So if you want what we have here is we have a u from W1, 1, 0tx. So we have one weak derivative, and this one derivative is an L1. So that is the most, in some sense, that's the most weak notion of solution, as long as we insist that now it becomes a little bit tricky, I admit, as long as we insist that all the image spaces are the same. So our typical image space would be the H1 or the H10 corresponding to the boundary condition for the underlying elliptic problem or something in between. That would be our H1. But of course we can vary also a little bit here with the X. We will see later, we will make this a little bit rigorous and more systematic later on. So what kind of possibility we still have? We also have the L2. And maybe it's enough that the initial data, first of all, it's a sort of a restriction to say that the initial data should be in H1. That is what we have to do at the moment. Maybe we would like to have initial data in L2, so we have to apply here, we have to work here also with a larger space. And there is an even more larger space, namely the dual space of H1. This dual space of X. In our case, then the H-1, the dual space of H10. And all these spaces will come into play. But here, if we don't do that, so that would be the most weak situation. And the assertion is this space has a continuous embedding into the space of continuous function. That is, that means the following. Let me write it in this way. After changing at a set of measure 0, a subset of the 0t interval, we have the following. The function u is a continuous function. Sometimes I write the interval in this way and sometimes in the other, or better to say Schweitzer does so and I follow him blindly. And then we have, and now for all, after this change, for all t1, t2, between 0 and t, we have the validity of the fundamental theorem, so we can compute as we are used to compute. Also, we have these very abstract notions here, so we can express the difference of u at t1 and u at t2 and u at t1. The difference we can express as the integral between t1 and t2 of the time derivative. So this is an identity, of course, there's an identity in X here, in the underlying Banach space where the spatial variables live, where the spatial aspect lives. That's not an identity in numbers. It becomes an identity in number if you now have a specific situation and say this is an H1 function, then you have here at x and so on. And then it holds true almost everywhere for all x in omega, or for all x in omega, depending on the underlying capital X space. Okay. We are not going to prove this now. All the proofs are a little bit technical in the sense that one has to find a way to handle with these non-smooth functions, and the way to do so is to do approximations. So we do convolutions. We do convolutions of our functions with a specific Dirac kernel, maybe very similar to what we did concretely in the last semester, looking at the fundamental solution being a solution for the heat equation with this Dirac distribution initially, and then seeing the solution is a convolution and so on. But what we want to have here is just to have here a little bit the notion of it would eat up too much time to do all the proofs, so we are satisfied in seeing a little bit the notions and the results we can apply. Okay, so what I indicated already is this. What I indicated already is the following situation. We have three typical spaces, and this we will now bring into play. We have, so to speak, so what we want to have is we want to have interpolation theorems. For time space functions. What is an interpolation theorem? Interpolation basically means we know. Okay, let me first write down a little bit of the example I have in mind and what is a typical example for our application of this general theory. So to speak, in the middle, as I said already, now it's not called X, it's called V. In the middle we have our space, let's say H10 of omega, if we have Dirichlet boundary conditions. Then the larger space we have is the space H, L2 of omega. And then on the other hand we have the dual space, which is just the notation for the dual space H minus 1. So what kind of properties? So the sequence is, of course, is this is the smallest space, this space is in the middle, and this is the largest space. And of course, both of them, now we have to be a little bit careful in the sense, both of these spaces are Hilbert spaces. They both have their scalar product with the corresponding norm and so on, and via the scalar product we have the duality pairing. The duality pairing is just an extension of the scalar product. And what one often does, if one only deals with the L2 space, one just says, okay, we identify this. So we don't distinguish between L2 being a function and L2 being a dual, an element of the dual space of L2. This we can do, and this we will do, but we can do it only once. We cannot say, okay, we identify the duality pairing with identity in the L2 and do it here. So what we have is the following. We have here in general the following situation. First of all, as sets. So the general situation is, as sets, we have Banach spaces. Let's say H V prime. So this notation already indicates that this is, in general, maybe that will be the dual of V, but we will also have more general situation where we don't need this this property. We have assumed that H is in Hilbert space. We have the following situation. V is the smallest set, then there is H, and the largest set is VH. And what we do is, as I said, we identify H with this dual. So this is the identity in the middle, so to speak. What we still need is V should be reflexive. V prime, that is something which sometimes one can omit, is the dual. And now we have a new notion, is the dual with a consistent structure. I will explain in a second what this means. Okay. And what still do we want to have? So these are not only set inclusions. With this identification, what we would like to have is, we have here at least a continuous embedding. That's what we have. We can estimate, if we have an H1 function, we can estimate the L2 norm, of course, trivially by the H1 norm. That is the continuity here. Because of that, because of this identification, we have here, of course, also a continuous. So this sign usually means continuous embedding. Here we have also, of course, the continuous embedding here with the V prime, if this is the dual. So now we would like to have a little bit more. We would like to have that the V is dense in H. This gives us the possibility, which is also true, that means here specifically we can approximate every L2 function in the L2 norm by means of a sequence of H1 functions. This is true. We can do this with even more smooth functions. Depends a little bit on the boundary situation. So that gives us the possibility, so to speak, to reduce considerations with H1 functions to H functions to functions in V, if we can then use such a density argument in the end. So what now means consistent structure? This is supposed to be the following. This is in principle what I have written down already here. It means the following. It means we do this identification, as I said. And then we have then with this identification, as a consequence of this identification, we have then also an inclusion of the dual space H1 in V prime, H prime in V prime, and on the other hand, we also have the canonical embedding. Canonical because namely because of this what I've already written down here, And the assumption is that these things are the same. That means the following: if we write down, if we have a function, let's say v in capital V, if a function u in H, then on the one hand side, we can interpret both of these functions, of course, in H, specific in the example in the L2. So we have the duality pairing, which has become an identity with which is the scalar product. So we have the uv in H. On the other hand, that's the same thing as interpreting this in the duality pairing of v prime and v. Let's just look whether the sequence is correct. U in H, yeah, okay. So this is in particular also a v prime element. It's in H, it's in H prime, it's a v prime element, and all this fits together. So this is meant by that. That's no problem with our examples. And if one has this situation, one speaks, that is the notation of a Gelfand triple. And then one can relax a little bit the assumption. One can speak of a Gelfand triple without duality. If one says this v prime is not necessarily the dual space, or we can. Okay, I missed one important assumption, which will be very, very important. It's here we do not have not only have continuity and density, we also want to have compactness of this embedding. So this then we see this later on how this comes to work. So later on we need something which converts our a priori estimates into convergence results of subsequences. So we need a compactness step in between. Compactness just means that a sequence which is bounded here, that would be the a priori estimate, has a subsequence which converges here. So this is just here for our example, that's just the classical Kontrativ-Rellich compactness embedding of the H1 into the L2. Okay, so we can have Gelfand triple without duality, and we can have Gelfand triple without compactness if in some situations this is sufficient. So, and now we want to take this freedom which we have here to consider the following type of situation, because this will turn out to be a typical situation which we get out of the a priori estimates. Why interpolation? This we will see later on. So what we will see later on, that we can, so to speak, that goes in the direction of inverse embeddings. Of course, we cannot expect that we can control. What is said here? We can control the H norm by the V norm, but of course it's not vice versa. But what will turn out is that we get a reverse situation if we bring in the so to speak, the third norm. So we will interpolate a little bit between these two norms. So that therefore this notion comes from, but we will see this later on. If you wonder why this is called interpolation. Okay, so now we take this situation and relax a little bit. So let's say Gelfand triple. So V, H, V prime, Gelfand triple. It can be relaxed a little bit, but it doesn't matter for our cases. We will always have this situation, this general situation. And we will now have a function u such that the function itself is an L2 function, so to speak, with, let's say, smooth images, with images in V, not in H, in V. So we have images in the H10, say. But on the other hand, the time derivative, and that will turn, so this will, we will see in a second, this will be an estimate we get quite naturally, and the drawback of the whole thing is that for the time derivative, we get, on the other hand, quite a weak estimate. And the weak estimate will be, we get only an estimate in L2 0t with V prime. So we don't have the that will be the technical point. We don't have the time derivative as a function. We only have it as a dual element. So with this situation we have to live. And this theorem now tells us, first, the nice thing is, that's not so bad in the sense. So this very weak time derivative helps us now in time in doing an embedding, in the sense we have a continuous embedding to the continuous functions, but now only with values in H. So that's what I meant. This gives us the possibility to impose initial data and even initial data in H, in L2. We don't have to do everything in the final step in the underlying space V, which is according to the nature of the parabolic problems where we have this immediate smoothing. So we expect that we are able to start with very rough data and then, so to speak, for every positive time t have then this smoothness. So this is not only a set inclusion, it means, as I said already, that the embedding, that is these two things together. So what do we have? So we have the function in L20 TV, and we have it also in W, not W, you can write it with H, H1, H10T V prime. So this gives this here, because if we have this, we also have also, of course, the same situation with values in V prime. So we have here the function and the time derivative belong to L20 TV prime. That is what's stated here. And this embedding into the continuous functions, this is continuous. So we can estimate, we not only have it as an element of the space, of the set, but we can estimate the maximum norm here by means of these two L2 norms. That is what is stated. So, and now if you remember what we did, so to speak, in a formal treatment, what we did in a formal treatment on the continuous level. We had our heat equation, we tested it with the solution itself, either starting from a classical solution or a weak solution, and then we had this term under the integral, time integral of u times u. And this we always then rewrite. We say, okay, that is nothing but the derivative of 1/2 u, the time derivative of 1/2 u square. In classical notion, there's no problem with that. But now we have distributional derivatives and so on. And the next statement is, this is okay. Also here we have exactly this situation. So if we do the following, if we do, now here the two is put to the other side. If I take in the underlying, so this is, if you write it abstractly, this is in Hilbert space, and this bracket is the scalar product in the Hilbert space. So in our case, it will be the L2 space. If we write here, doesn't matter, the ut for fixed instance of t, time derivative. So this is what I just described. What we end up, and this is the abstract version of this, and this we can now write as the time derivative of the ut the norm of ut in what is it in H? Sorry. So we can do this transformation always. So we can now also relate to the notion of absolute continuity. Maybe I skip this. Let's see what still do we need. So as you see, I just mentioned here the results and do not do any proofs. What we still need are two things. The one which I also indicated, which is the so-called interpolation estimate, where the name of this triple situation comes from, what I already tried to describe. Okay, one can reduce a little bit, as I said already, the assumptions, but I'm not going to do that. I'm just saying Gelfand triple as above. So some things can be avoided. It's not so important now. You can look this up. And now we have the following situation. Let me first write it down. I just give me some constant eta, meaning that's a small constant. And the notion is for each of these constants eta, there is a constant which then will be, say, a big constant, C eta, such that we can do the following. We can estimate the H norm by means of eta times the V norm. So, of course, we have an estimate of this type, but for a fixed, this is just a continuous embedding, but for a fixed constant here. Now we would like to make this constant as small as possible. Because if later on we will use this in what is called an absorption argument, so we have terms in our estimates on the right-hand side, which we would like to integrate in corresponding terms on the left-hand side, in terms to be estimated. But of course, then the constants which appear here must be smaller than the constants on the other side. So it's not sufficient to have here any constant. And the assertion is we can make this constant as small as possible if we allow, on the other hand, say with a large term, but now in a weak norm, now in the V prime norm. So in this sense, we have an interpolation of the H between these two spaces, the smaller one and the larger one, and we can shift the weight between these two spaces, how they appear. So that is the one thing which we need, and the final thing is the theorem of Lyons and Aubin, and there is other versions, and one is, I think, on the homework sheet. And this says the following. We started already with in our notion of the Gelfand triple with, so again, Gelfand triple with this very important requirement of compact embedding of the V to the H. The question is, how does this now transfer to the time-dependent functions? And the assertion is the following. If I have a function which is L2 in V, and which is, where we have it already here, and we have it, which is H1 in time, but with values only in the dual space. So we have a time derivative, but only as a dual element. Then here we have seen, we have a continuous embedding, but only a continuous embedding to the space of continuous functions with not so smooth images. this assertion says that if we further relax and now look at L2 0t h, which is of course now also a continuous embedding, if we go from the continuous functions to the L2 functions, then this embedding is even a compact embedding. So this will be the key for doing then the convergence step in our proofs. So we will have these estimates, and by this we will get strong convergence in L2. So the question is, do we have to work with weak convergence, or can we work with strong convergence? And all the boundedness in Hilbert spaces and in reflexive spaces only gives us weak convergence. That is, that's the definition of being a reflexive space. So we know in a Hilbert space and a reflexive space, the ball or any bounded, any closed bounded set is weakly compact in the sense I can select a subsequence which is weakly convergent. Here, this allows me now to select a subsequence which is strongly convergent in this space. Okay, with values only in H, but anyhow. And this will be of strong importance if we then finally will go from linear problems to nonlinear problems. Because within linear problems, we always have the possibility to see everything in the realm of distributional derivatives, and we can come along with weak convergence for a long time. But if we want to go through nonlinearity, so to speak, we need strong convergence. And there's another place where we need this, namely if we ask ourselves, okay, do these limit functions, which finally we will get out, and which then hopefully fulfill the equations, do they also fulfill the initial data? And therefore we would the initial data in H, and then we need something like that. Okay, so this is, so to speak, these are our tools now. And now we can start, or go back to what we started already, namely the proof. So what we are going to do, we approximate in time by discretization in time. We have the implicit Euler method. We have a sequence of solution of the corresponding elliptic problems. We know that these elliptic problems u to the n exist. And now we would like to form functions in space and time out of these, would like to see in which sense do they converge, and is this limit then a solution of the underlying heat equation. And then, of course, with the aim to have an approach which then can be generalized to all kinds of variations of the heat equation. So we summarize the whole thing again. So what we need is, now in the specific case, in the summary is the following proposition. That is the so-called, Schweitzer calls this the compactness, Trickkiste, whatever this means, magic box. So in principle, you don't really need this all this Bochner theory. You need only what is said here. And now we apply the whole thing. So what do we have? We have our domain, small n. We have our domain, our bounded domain. I would say, yeah. Let's assume that boundedness is included in the domain. We have our time interval. We have our space-time cylinder. So and now we assume that we have a sequence of functions, u capital N. So this capital N is the index. U capital N is supposed to be a sequence of functions, can be also be vector valued, which is bounded, it's bounded in L2 0 T H1 0 omega. And we will see that is what we get out by the energy estimate, this kind of a priori estimate, this bound. And then what is the consequence? The consequence is that is now knowing that this is a what we know this is a reflexive space, and because of that we know boundedness implies weak convergence, and therefore the first conclusion is there is a function in this space such that there is weak convergence. Let me see how I write this. It's always for a subsequence, but maybe I suppress this a little bit because otherwise I get a too clumsy notation. It's always for a subsequence. For a subsequence we have weak convergence. That means weak convergence is we put this in the dual pairing. So here we have the UN. Here we have the test function. This converges then for the corresponding term here. So this bracket here is the bracket of L2. That is the underlying H, that's the underlying pivot of the whole thing. And the test functions which we can allow, is all the elements of the dual space, and the dual space we have identified as the L2 0T H minus 1 omega. So that is nothing but the statement of weak convergence here. Now, that's of course not enough. We want to see something for the time derivative. Additional estimate now for the time derivative. So if the corresponding time derivative sequence so yeah, what does this mean? What an argument always is, if we have such a weak convergence, we also have this weak convergence even for much smoother test functions, so to speak. So we always have convergence as distributions. And this is important because we know for distributions, first of all the rules, all differentiation rules hold true because we just put it to the test functions. That's one thing. And the other thing is the limit of a distributional sequence is unique. So if we have sequences which converge in different notions, the trick will always be to refer all to the distributional sense and see, okay, but there's uniqueness, and therefore these different notions of solutions have to produce the same limit. Okay, so what do we know? If this sequence is bounded, so that's another case of an a priori bound. Now for the time derivative, if we get such an a priori bound for the time derivative, and now in L2 0t, but only here in the dual space, so not as functions, only as dual elements, then okay, then that's not stated here, but I think it has to be true. Then also the derivative of the limit, which you can view as the distributional derivative, the derivative of the limit has to be in this space, and correspondingly there is also weak convergence. it's exactly the same argument. We now look again at this space as a reflexive space. So this is now the starting space, and the dual space is correspondingly the H10. It's just the situation reversed, and because of this reflexibility, there's a sort of symmetry between x and x prime. We can go back and forth in both directions. So basically, it's, I state it again explicitly. What does this mean? It means if we have here these time derivatives, again, of course, for a subsequence, if we have here these time derivatives, if we have here the corresponding test functions, I will say in a second what they are, then we have the convergence to the limit here. And now the psi, the test function psi, for all psi from where? The corresponding dual space now, and the dual of this one is 0t H10 omega. But this is still enough to, this is now more restricted here with the test functions, but still enough to have, as a consequence, the notion, the distributional convergence, and so to speak, to have the comparability of all these notions of convergence. And then finally, by the compact embedding of the space, then we have also the strong convergence of un to u, so that is in L2 0t L2 of omega. This is now here the h. So this is just a direct application of what we have discussed, and these are basically the reasonings what we will apply. So a final tool I hope you will know, and therefore I think I will skip the proof, is the so-called Gronwall inequality. Who has never heard this notion? Okay, good. Okay, then I explain it a little bit. You've never done ordinary differential equations? Yeah. No existence proof for ordinary differential equations? No? A little bit. Because there you... okay, it doesn't matter. It's not very complicated. The Gronwall inequality. There are a lot of versions of the Gronwall inequality, and there are continuous versions and there are discrete versions. And the basic continuous version is the following. Let's say we have a y, a function y, let's say just very simple, it's just an integrable function. And let's assume this is the function we would like to estimate. That's a norm of something. Therefore, it has reals here. And let's assume that in our energy estimation, we will end up with something like an estimate of the following type. We can estimate this function by something which is given, which is good. So if this would end like that, that would be a good, so to speak, a priori estimate. But now the thing goes on, namely in the sense that here on the right-hand side, again this function appears. But it only appears as the integral. It appears in this form here. And the question is, what can we conclude from this situation? Is this enough to give, nevertheless, so to speak, an a priori bound for this function in terms of the y and the t, but of course not the y itself? And okay, if this would be an equality sign here, so the extreme case, so to speak, then I think we know how to conclude. Because then we could take the derivative and we could get, we try to view this y as then as a solution of an ordinary differential equation. So the initial data is y0. And if we look at the derivatives, that's y prime equals y. And that's, of course, an equation which we can solve. And then we have the solution. The problem is, with the inequality sign, that's, of course, not compatible with taking a derivative. You can take an integral and preserve the inequality, but you cannot take a derivative. So one has to argue differently, but the conclusion, as we would expect it, holds true, namely y of t is less, not equal now, but less or equal y0 e to the ct. And this can be very much generalized in the sense that there might be functions here involved here. If you really would like to have these functions still there and not estimate them again by a constant. Yeah, okay, I forget the constant c here. Estimate them by a constant. And then you can do the same thing also discrete in time. So then you would not have here a time integral, but you would have a corresponding approximate integral, a sum, and similar things hold true. Okay, so do we have it on the exercise sheet, this thing? Yes or no? Huh? Not on the first one. I think, okay, if I'm a little bit shocked that you have not seen this. Because it's really, as you see, it's an ODE thing, which then, what we are doing here, so to speak, are ODEs in Banach spaces, and therefore these things come together again. And let me indicate how the proof works. Sorry for that. Maybe we can get a better room than this one here. So the proof is the following. So we look at the function wt, which is this integral, which we have on the right-hand side. What was the notion y? So now, what does that mean? That means that w prime of t, this is the y, is less or equal than wait a second. What did I do here? Okay, let me phrase it a little bit differently. I claim it's sufficient to prove the following. It's sufficient to prove a special situation. So this I leave to you to check out that it's really sufficient to do that. I claim that's sufficient to prove. So what I do is, so to speak, I leave away the y0. I claim it's sufficient to show the following. If I have a function, then now let's call it z, which fulfills this condition. And then this function is always smaller than 0. Let's assume that we can reduce the statement to this statement. Now we do the following. We look at the primitive, and for this primitive, if I just look at this function, what does that mean? The w prime is just the set, so the w prime is smaller than cw. Now I have transferred this integral inequality to a differential inequality. So now I do the following trick. I multiply with, I bring everything to one side, and multiply it with this term, x minus ct w prime of t, and in the other term minus cx minus ct wt. And all these things are smaller or equal to 0. So why does this help me? Because now the terms of what I've basically done, I've multiplied an integrating factor, because what I have now on the left-hand side is just the derivatives, just check this, from e minus ct wt, and from this the derivative. If I put the derivative on the second term, I get this. If I put it on the first term, I get this. And this is smaller or equal to 0. So, okay. So the initial value, so what does that mean? That means that this function is decreasing. And that, of course, writing this down means that x minus ct wt is smaller or equal than x at 0. If you want w at 0, this is a 1, and the other thing is smaller or equal to 0 if I plug in here this. So both are both. This is a 0. So okay, and then I'm basically done. That means the w of t is negative. So that means now I rewrite what this is. Set of t. S, or let's say S, ts is negative, and then I plug in here the set of t is negative, non-positive, okay. So, and that is, yeah, all the general forms can be sort of reduced to such reasonings. If you would like to see it in the general form, the Gronwall inequality. So let me put it another way. For everything which is concerned with ordinary differential equations, and ordinary differential equations are a very general notion in the sense, because in this book everything is done Banach space valued with a view at such evolution equations. And that is the book of Herbert Ammann, Gewöhnliche Differentialgleichungen, or in the translation, Ordinary Differential Equations. This is the book about ordinary differential equations. You don't have to go to all the other rubbish which exists. You only have to look at this book. So this is Gronwall inequality. This will help us. Of course, it has drawbacks. The result will have drawbacks. What will that mean? It will mean that in our estimates we will get out. We get a time-dependent term in. A time-dependent term which increases quite a bit here. That means our estimates are not uniform in time. And if we would really think in them in terms of numbers, it might well be that they are not very helpful for large intervals. But anyway, so now let's see what we can do. So I remind you what our approximation was. Our approximation was the implicit Euler method. And that was the following. We start, of course, so we have our distribution in time, our TKs. We start at T0, which is 0, with a U0, which we assume here at the first step as being H10 function, that we are in the space where the whole solution should live in space. So this is something which later on has to be removed because that's a much too strong assumption. And Euler method means now at each time level we require let me wait a second. Sorry. The notation is this here, and we have the index below. At each time level k plus 1, we require that this time derivative, this difference quotient substitutes the time derivative, so we have this elliptic equation for uk plus 1, and this we have a time stepping which produces us the uk, and of course the uk's exist uniquely in H10. So now how to make functions out of that. So we have two possibilities to make functions out of these, so to speak, discrete, let's say, points in time. Either we make a piecewise constant function out of that, because we can make more complicated things, but that's sufficient for us. We can make a piecewise constant function. So this function we will call u tilde n. So this is now a function from 0t to h1 0. And it is defined in the following way. It's, so to speak, piecewise constant. So we have here our interval. We have here our equidistant distribution in the t case. And here we take the u0. This is now indicated as points. Of course, these are elements of the Banach space. On the first interval, we take, so to speak, the value u1. Then here we take the value u2, and so on. That's the most simple way to make a function in time out of that. So we have here u tilde n at t is uk plus 1 for t from this interval tk plus 1. That's one possibility. That's simple. The problem is this function does not have, this has a time derivative, a distributional time derivative. But what is the problem with the distributional time derivative of this function? Where is the problem? Okay. This, of course, every L1 function has this. An L1 function, every L1 function has a distributional derivative. But then we get Dirac parts into that. We don't have a function as derivative. So if we want to have a function as derivative, we must the minimum is we have to make, you remember this question with the finite elements. When do finite element spaces belong to H10? It's in space there, but it's basically the same question. And then you have, then the conformity comes up. The finite element have to patch together continuously. Otherwise, we would not get H1 functions. We would not get the derivatives as functions. We would get Dirichlet parts. And that's the same thing here. And therefore, if we want to avoid this, and we have to avoid this if we would like to deal with derivatives, then we take again those values, u0, u1, u2, and then we just interpolate linearly. So that would be the other possibility. So that is piecewise constant. And we give this a name, this space of piecewise constant functions, we give a name. We call this function then, the space is then supposed of this type is, for further need, is called Vn. And now we make it piecewise linear. And then we get the function un, so you have to distinguish between these two functions. Piecewise linear leads us to un. The space then we will call later on wn. And the definition is just affine linear interpolation, so the un of t is just a linear function in t which connects the uk and the uk plus 1 and for the corresponding convex combination of the t in terms of the tk and the tk plus 1 in the corresponding interval tk plus 1. Okay, so these two functions we have. And now what about the a priori bounds? Okay. So how did we do that in the continuous case? We just tested with u, and what we now do is we test with uk plus 1. What does that mean? Where is it? Where is it? Oh, mommy. What do we get if we test with uk plus 1? We get here in L2 norm, with this factor 1 over t, we get here an 2 norm squared. We get here, think of that in a weak notion, we get here the derivative part of the h1 norm. And then we get this mixed term with uk plus 1 here. So what we get is the following. We get 1 over tk, 1 over delta t, as I said, uk plus 1 squared. So if I don't add anything, it's always the L2 norm. We have this mixed term. And here we just have, we bring it to the other side. We just have, as I said, the L2 norm of the derivative, so minus gradient of uk plus 1 square. So what can we do with this term here, which is a term? So the typical estimate will be, of course, to estimate this what we do typically with functions like this here. We want to separate this. Of course, what we do is we apply the Cauchy-Schwarz inequality. That is, we get here norm times norm. And here this term, typically these terms are of a type that one of these things we would like to control. So we would like to have it with a small factor to absorb it at the other side. And the other, okay, we have to live with. So we can. So one version would be with a binomial theorem, not sure whether it's a theorem, but anyway, would be just this thing here. So this is the separation just with what do we have? AB, 2ab less or equal a squared plus b squared. But of course we can, maybe for further notion, what we can do is we can have here, so to speak, epsilon times, or square root of epsilon times epsilon to minus 1/2. And we plug in these factors here. So we will get here, let's say, an epsilon u square. So this makes it as small as necessary to absorb it. And then we have to live with the fact that we have here this term here. So that's the way to separate these things. And this means here we get now the following. And now what we do is we have all these estimates and we add them up and multiply the whole thing with delta t. Adding up and multiplying with delta t, for having these functions in mind, just means to integrate the integral in time. So we get here the delta t and the sum of those gradient terms. So these gradient terms have the right sign, so they are in principle good. And then we get, maybe I do it in one step. Or let's do it in two steps. Then we have this sum of the L2 norms. And then we have this mixed term with the minus sign. And this we estimate from below, and that is sufficient here to take this 1/2 situation. We estimate this from below, and then we have here leave this 1/2. So I get minus 1/2 of this guy, so this goes away, and I have minus then of the UK. So I still have here UK plus 1 squared minus UK squared. So now if you look at this sum here, this is a telescope sum in the sense that going from part to part, one of these two terms cancel with one of the others. And the only thing what remains is the smallest negative one, that is with the index 0, and the biggest positive one, that is with the index n. So what in the end remains is the following. We have here this thing minus this thing. So this is just data. And you see that there's some space in between. Here only we need the L2 norm, but we have assumed that it's an H1 function. So this gives room for further move. And so what can we do? We estimate for every instance in time here. So for every instance in time, we estimate the L2 norm by means of this initial data. And we not only estimate the L2 norm, if we bring this negative part also to the other side, we also estimate but not for each instance in time, but only as an integral in time, the spatial L2 norms squared of the gradient. So how do we write this? If we now apply Poincaré, with Poincaré tells us we not only can control here the gradient, we control the full H1 norm. So with Poincaré, we have here something like, let me write it in the following form. We have something like the integral in time of gradient u tilde n, the piecewise constant version, in the L2 norm, because these terms are nothing but delta t times the sum. Plus pointwise in time. Okay, changes a little bit. Plus pointwise in time. Let's say tk. There's a small argument still involved, but I skip this. And this we can control by some constant, which now Poincaré comes in times the initial data. And as I said, Poincaré comes in. What I can here substitute, I don't have to have this thing. I just take the full H1 norm here. This is where Poincaré comes in. So what I have here is an a priori bound. If you have here an a priori bound, for these piecewise constant approximations. Where are they? So what do we have? We have L infinity 0t H1. This is this thing here. We control all these values, and these are all the values of the piecewise constant functions. And we have L2. We have now the time derivative. Where do we have the time derivative? No, sorry. That's nonsense. L2. This is this thing. And we have L2, 0t, H10 of omega. And now, of course, there's no time derivative is missing. But the problem, as we said already, here we cannot work with the time derivative. Now we have to look at this kind of function. And now if we look at this function, and if we now look at the un without the delta, the piecewise constant, what is the time derivative of this? The time derivative is just 1 over delta t uk plus 1 minus uk, something like that. So the delta t is something fixed. Let me see it. So what we have, no, we have to, yeah, what can we do? Can we see, yeah, okay. So what is now the point? Now we could argue, okay, this we can control, this we can control, everything is fine, but there's of course the 1 over delta t. And this will explode in the limit process. So this will not help us. So we cannot now just say, okay, there is a corresponding estimate for the time derivative. We have to get the time derivative implicitly from the equation. So, but what are the equations? So if I now look at this part which you now don't see here, so if I just write down here, just copy the equation again, I can substitute, as we have just said, the difference quotient by the time derivative of un, and here we have the Laplacian of u tilde n. So we said we have bounds here. What kind of bounds do we have for this type here? As we have here, for the first derivative, we have a bound in L2. That is what's stated here. What we have here is we have a bound now in the dual space in L2, 0t h minus 1. And because of this identity, we also have a bound in this space for the time derivative. So we have to, because, yeah, this is, we cannot just ignore the delta t gets smaller and smaller, and the consequence is that we have to work now with these spaces. So what we have here, and that is what we then have to finalize next time, is we have to here to deal with these two different functions, see how they converge, see how this convergence goes through this equation, and finally, of course, that also the limits are the same. And then if we have done this, then we have found a solution at least of the equation in those spaces which we discussed already. And the only last step is then the conclusion that there is also the initial data fulfilled. Okay, so this we have to do next time.